Aldo, if you have anything else to say. Okay, so that's it. Thank you, Nadia, for being here. And yeah, you can start.
Okay, well, yeah, thank you for inviting me to give a talk today. It's a pleasure to be here. It's a very nice department. So yeah, I hope to give you some insights about binary evolution, and especially the phase of common envelope. I would say, why is it important, and how we can use these luminous red nova transients to learn more about this phase, which is very important for the formation of compact binaries, but it's a real challenge for theoretical astrophysics. So yeah, first of all, I'm going to talk about binaries, so systems with two different stars, like you have two different masses that evolve at different paces. And we can ask ourselves, like, why do we care? Well, we do care because as we go up in mass towards more massive systems, the binarity fraction increases. So for stellar sort of sun-like stars, it's below 20% the stars that are in binaries, but as we go to higher masses, and these are the masses that create neutron stars, black holes that we see through gravitational waves, for example, these stars tend to be born in binaries, and they're such a short distances that they interact. And we care about the interaction the processes because the byproducts of this interaction actually create marvelous astrophysical systems that we really love to study. For example, binary interactions create type 1a progenitors, stripped core collapse progenitors. They also create lots of CSM, which can interact with a posterior supernova, or also be related to extreme eruptions for like supernova impostors or LBV stars. But then if one of the stars explodes as a supernova, it can create black holes, which are like at very short distance, so that actually gravitational wave emission is important, and they can end up in a merger that we can observe right now with LIGO Virgo, for example, or compact X-ray binaries that people here also study. But moreover, also the naked cores of these binaries, they also can help to ionize the medium and maybe the cause of the ionization of the universe, or also the source of ionization for this beautiful planetary nebula that we also see that, interestingly, they are not spherical, but rather show these bimodal morphologies that I will explain a bit later. So this is the big question, how do we get from a really wide system of years orbital period into a short configuration? So for example, there is this binary that was likely born with a period of 10 years, but right now we observe it as a carbon oxide white dwarf and a main sequence star with half a day period. So in the 76, Paczynski proposed this mechanism, saying that when the more massive star would expand in radius so that the actual orbit is inside this star, a common envelope would be formed around this system, so that then the drag, or like the angular momentum from the orbit, can be transferred to this envelope, and then eventually the envelope will be ejected and will be lost, and we will be left with the core of this star and the companion. So this is the common envelope phase, and it's necessary for the formation of compact binary systems. So then what are the phases? Oh, let me just move this out. No, doesn't want to go out. So what are the phases of common envelope? So as I mentioned, we start with two binaries, and then one of them grow. And we can think this as kind of containers with water. So one of the stars, when it grows, it starts transferring mass, and this is the Lagrange point number 1. So it will start transferring mass up to the point that it will fill the container of the companion, and then we will have a contact binary. I mean, it doesn't necessarily mean that the system will become unstable, So then the question is like, which one of these binaries will actually become unstable, and which ones will actually detach and continue evolving separately? So then in the next stage is that in the case that this is unstable, imagine this keeps growing, we will start losing mass. So the lowest next Lagrange point is this L2. So the first mass will be lost from here and then from here. So if we look at this binary, like basically we'll have a trail of mass that escapes from the system carrying a lot of angular momentum. And this loss of angular momentum actually will contribute to the tightening of binary and very fast timescales. So then the question here is how the binary loses its angular momentum. The next stage is finally the stop of core rotation. So basically the binary initially will be kind of locked, but then eventually the envelope of the primary will stop co-rotating, and the secondary will kind of spiral into the envelope of the primary star. And this is the moment of the formation of the common envelope. And the final stage is the transfer of the binary energy into the envelope, so that if the envelope is still tightly bound to the system, then the system will merge and will just eject a little bit of mass. But if it's something like a red giant or AGB star, then we can actually help to combine the whole of the envelope. So then we will actually have a surviving binary system and all the envelope kind of flying around. So then the question is how the envelope gets ejected. So what energies come into place to eject this full envelope? And also we care about like what kind of, for example, geometry this ejected envelope has, and how we can tie this geometry to systems that we see nowadays. So we are lucky because the actual ejection is a transient, and we can observe it. So this is one example of such transients. This is the V838 Mon Luminous Red Nova, and this is a light echo that was transferred into surrounding gas. And we can see this Luminous Red Nova with ground-based surveys. I think there's quite a bit of people working on time domain. So you're probably familiar with the Zwicky transient facility, but maybe you haven't heard so much about BlackGem. This is a new survey starting from last year. We had like an official first light, I think 2 weeks ago. So then we can monitor the sky on a regular basis. We can detect this transient, build the light curves, see their color evolution, for example, and follow them up spectroscopically. So actually we can learn how they look like, what are the ejecta properties, what elements do we see there. So if you are familiar with classical novae, for example, or core collapse supernovae, the luminous red nova population sits around here. So that's why they also called gap transients, because they are in this gap between supernova or nova or intermediate luminosity transients. Although the nomenclature is very confusing still, because there's like other types of transients that share the same parameter space. But for the moment, let's see that they are kind of here in the middle, and they look like a bit like a banana, right? Because there is like some correlation between how long they last. So this is like a few tens of days, 100 days. Some of them last up to a year, and their luminosity. So the longer events are also the brighter ones. And for a survey such as ZTF, for example, we can actually detect that the brighter ones up to 100 megaparsecs. So if we look at the sample of light curves for these transients, there is a huge spread in their luminosity, but they all share like a similar pattern, and there's like a quick short peak, which tends to have like hotter temperatures, and a longer plateau or secondary red peak. So what the spectra tells us about this? During the first blue peak, what we see is a very hot continuum. So if you look at here, this is an optical spectrum, wavelength and flux. So basically the peak of the emission is somewhere in the UV, and we see a lot of electron scattering, meaning that basically there's like all the layers are ionized, so the light is kind of scattering through those layers. But as the time passes, this hot gas starts to recombine. So we actually see colder photospheres similar to like an F or G type star. And a very late time, the photosphere is so cold that we start to form molecules, and this is the dips that we see in the spectra, which show that it's a very expanded and cold photosphere. So basically the outer layers are just peacefully expanding, cooling, and recombining. And this is kind of the ultimate evidence that this is this type of transients, because there is no other source of heating for this ejecta. It's just peacefully expanding and cooling. So then let's go to our first questions. How can we use this luminous red nova to ask this first question? So which binaries will become unstable? I mean, this is important because in the context of gravitational wave sources, we want to know which binaries underwent this common envelope. So they became unstable, they ejected common envelope, and they survived, meaning that there is still a binary there. And then the second component can also experience another common envelope, so we can bring the systems closer, and the supernova, if they didn't disrupt the system, it will be a binary black hole that will end up in a merger in a Hubble time. So some of these works explored very detailed stellar evolution models. This is, for example, for SMC metallicity. And they came to the conclusion that common envelope, full common envelope was only possible for stars which were red supergiants with very expanded, deeply convective envelopes. Anything else would end up in a merger. Similar works also explored, like, for example, for a 30 solar mass star, if it would have a black hole companion from like 0 to 20 at a different orbital periods. So this is more like 1,000 something days. We see only for the longest periods, we can have any opportunity to actually eject the envelope and not merge. And this is accounting that all the orbital energy from the binary actually helps us to release the envelope. If the efficiency shrinks down to lower values, we can see the proportion of kind of possible configurations for this binary that fully ejects the envelope shrinks dramatically. And this has huge implications on, for example, the rate, the creation rate for these gravitational wave progenitors. So then with Luminous Red Nova, what we can do is to observe these transients, and then from the properties of the transients, we can infer the ejecta masses. So if we have some knowledge about what the progenitor was, we know if it was a merger or not. So at the moment, we can start kind of populating this diagram. So how do we do that? Well, if we discover a luminous red nova in a nearby galaxy, we can be lucky and look if there is some archival data. If this is the case, then we can recover some of the colors for the progenitor star. This is, for example, people are doing with this nearby supernova in M101. And then, well, later on, if that star disappeared, then, of course, that was the progenitor star. So then we can model, for example, the spectral energy distribution and put it in the HR diagram and see where this star sits. And this is great because, I mean, this star actually sits in what's called the Hertzsprung gap. And the Hertzsprung gap is a very sparsely populated area in an HR diagram when the star has finished hydrogen burning in the core and it starts to burn hydrogen in the shell, but it hasn't ignited helium yet. So that means that basically the star is in a very quick expansion. And if there is a companion nearby, it will drop a huge amount of mass. So the system is very likely to become unstable. So just as a reference point, this is 3,000 years. It's how much it takes these stars to kind of cross this. And this is nothing in the life of a star. So if there was a companion in 3,000 years, then, there's like a lot of growth. So then, yeah, that also is confirmed by more progenitor detections of luminous red nova, which all seem to be sitting here in kind of the gap. This is the main sequence, that's the end, and the red giant fraction is here. But then the next question is why we are only seeing progenitors here? Why we don't see them here? So one of the reasons is in this work that actually explored the phase of previous mass loss in the system. And because the system don't just merge, there is a previous stage that I will explain now. There is a dust formation in the system as well. So basically, this is the extinction in the system at the moment of the merger or common envelope ejection. And we see that for these more extended envelopes, which are the ones that are full common envelope ejections, the extinction is about 100 magnitudes in the visual. So basically, we're going to completely miss them in optical surveys, such as CTF or BlackGem. So we need to go to the infrared, mid-infrared, perhaps, to actually be able to detect the systems. So then the next question is also, we know that this star was in a binary. So how the mass transfer actually can influence, the evolution of the stars. So this is something that we explore in this work. We had a progenitor for this system, which was sitting here. And if you just use single stellar evolution model, it would look like an 11 solar mass stars. But we know that if it was related to one of these luminous red nova and ejection in a binary, the system should be a binary. So then which binaries actually would be consistent with it? And what we saw is that more massive systems, like from 12 to 16 solar masses, were consistent with it. And it's because when you start transferring mass, basically the luminosity of the system drops. So the star, as it's giving mass, it tries to readjust to its kind of equilibrium. So basically, it loses part of this energy in actually growing and expanding and trying to readjust rather than luminosity. So basically the luminosity of the progenitor drops by a lot. So this is the time since beginning of Roche-Lobe overflow when it started to transfer mass to its companion. And over here you have the mass transfer rate per year. So as we can see, the system can be kind of transferring mass for centuries. So this is what we call like semi-stable mass transfer because it doesn't happen on dynamical timescales, but you know, it can last quite a bit. But at the end, the mass transfer rate is so high that likely we're going to fill, you know, that container for the binary, and we're going to spill the gas out of the system through this L2 and L3. And of course, this mass transfer rate is associated with a shortening of the period because there is an escape of angular momentum. So Luminous Red Nova again is a visual kind of witness of this process. And for example, this system, B1309 SCO, is one of the Rosetta Stones that allowed us actually to correlate these astrophysical transients with their cause. And it's because this transient was in the Ogle field. So Ogle was monitoring for many years, and Ogle has a very good photometric accuracy. So then when they saw that first the system was brightening, but then there was a lot of scatter. In this paper, they just folded these light curves, and they saw that they had a periodicity related to an eclipsing binary. And it was very interesting to see that actually the period of this binary decreased exponentially just before the outburst. So this is the kind of the Rosetta Stone, which allows us to put together these transients and their cause. We haven't seen anything like this so far, but we really want to detect something like this either in our own galaxy or somewhere nearby, because that would allow us to study more systems. But then what happens with this mass loss? Well, when you have the mass loss, it tends to wrap, and then you know this matter tends to be released faster. Then there is like self-shocks. So then finally there's like some emission from this kind of decretion disk that is formed around the binary. And that can also act to modify the visual appearance of this binary. So for example, this is the period again, this is the binary. You will see how mass loss is released from the system. And this is the kind of the signature of the eclipsing binaries that we saw that it was changing shape in the case of this V1309 SCO. And this could be actually explained by the fact that if mass is being lost, if the stream is thick enough, then it will end up kind of obscuring the small star. So then this kind of bimodality will disappear, we only will see kind of one half. So then this is great because, yeah, in this case, Luminous Red Nova is the kind of the instrument that allows us to test the decrease in period or loss of angular momentum with the mass loss in the system. And yeah, all this emission, which is called precursor emission, tells us that it's actually associated with L2 mass loss. So then do we see it in other objects? Yes, we do. This was an object from 2015 in M31. And the other one was in M101, so the same galaxy as now there is this type 2N, I think that was the latest classification supernova. And like both objects, like this 2 years before and 5 years before, we see that there's a gradual brightening in the progenitor system, which leads to the outburst. So this actually tells us that L2 mass loss is probably the dominant channel in these systems, versus other ones, such as, for example, Darwin instability, to actually drain quickly in a matter of years the angular momentum from the system. So as long as you start losing mass from L2, the merger is imminent. So then can we use this information to find luminous red nova, for example, in the Milky Way or in other galaxies? So we tried to do that. We localized, for example, all the Gaia stars that were kind of presumably sitting in the Hertzsprung gap, and we looked for the time variability. We identified some of the sources that seem to be going up in luminosity in like long-term in ZTF data. And then we took the SCDs and some low resolution spectra. I mean, I don't think we have any very secure luminous red nova progenitor yet, but it was very interesting to see that many of these sources showed actually infrared excesses, which are likely related to disks, such as ionized disks in B stars or colder disks in binaries. And they also had H-alpha emissions. So there were like some processes occurring there that would ionize some of these gas. So this is an ongoing project that my postdoc Hugo is working on. So he's looking at HST photometry in nearby galaxies to actually build a catalog of potential sources which are in this Hertzsprung gap that can eventually become this luminous red nova in a matter of few years. Yeah, as I said, we didn't find a luminous red nova, but we actually we predicted an outburst from a new B X-ray binary. So we saw one of these light curves in ZTF, and we said, oh, look, it's going up. Maybe it will become a luminous red nova. We took a spectrum and everything. But then there was a bit later, there was an ATEL saying that it was a maxi hard X-ray outburst. So actually it became a new high mass B X-ray binary. So we predicted something. So I mean, the method works, maybe not for luminous red nova, but for some other interesting transients. So the next question, like when we have this final drain of angular momentum and the system gets close together, how the envelope gets ejected. So this is something that has been widely addressed by hydro simulations. And here I will show you an example. Like this is the companion and this is the core of the expanded red giant. As you can see, that's like 100 solar radius there. But one of the problems is that these simulations struggled to unbind the envelope. So it seemed that this orbital energy, see this assumption that if you put all the orbital energy into the envelope, it would release the envelope, was failing for some of the groups because they would not, there would be fallback and then eventually the system would merge. So there was a new source of energy that was needed. But for illustration purposes, I think it's good to watch more or less the evolution and how the binary actually, the separation of the binary decreases. Of course, this is nothing but a smooth ejection. It's not very well. In this case, there is not even a pre-existing disk, but yeah. So here came into some other papers that claim that actually the recombination energy was one important factor in helping to actually unbind the full envelope. So this is the evolution of the ejecta in days, and this is the radius, and this is the ionization fraction for hydrogen, helium, and double ionized helium. So what we see is like basically the upper layers, when the time goes by, they start to recombine, but the internal layers are still ionized. So that means that as long as they will be recombining, they will be creating these low energy photons that still will be pushing away the outer layers. And moreover, if finally dust is formed in some of those layers, we can still have radiation pressure on the dust. So that can help to finally unbind the envelope. So actually this was used to build models for light curves, because what we see are transients with some duration, some peak luminosities. And what we want to understand is, for example, how is that related to the ejecta mass from the system? So for example, these models explore the possibility that these luminous red nova transients would be powered only by recombination. So this first initial would be a quick release of thermal energy of this heated gas in this shocks ejection. But then this long plateau that we saw in the light curves would be powered by individual shells, which are recombining, kind of similar to type 2 supernova, that would actually power this longer plateau. So then the recombination from would go inward and we will have this long light curve. But there is a problem. This model cannot explain the most luminous red nova that we see. And this is the donor mass, the star that ejected the envelope, and this is the ejecta mass, and this is one-to-one correlation. All these objects sit below, but the more energetic ones, you need an ejecta mass, which is higher than the donor mass. So something doesn't work. So we need an extra source of energy. And we think that it comes from shocks. So there is additional models that are based in that during this L2 mass loss, the binaries are not alone, but they already have created some wind, some kind of this decretion disk. And when the quick ejecta is released from the merger, it crashes into this disk. So there is a lot of shocks, and shock can be very efficient into transforming energy into luminosity. So then just a little bit amount of interaction can actually explain the extra luminosity that we see in these objects. So then the same, like there could be like some quick peak here released by the cooling of the envelope, but then a secondary this plateau or long plateau could be also powered by shocks. So which mechanism is the dominant is still to be seen. We need to run some rates and modeling for more objects. And yeah, the final question is also, okay, now that we know that we have several energies that come into play into this envelope, then what is the ejected geometry? So how this envelope gets ejected and how we can relate this ejecta with other things that we see now. For example, how we can connect with planetary nebula. We know that 20% of planetary nebula actually have a compact binary in their cores. And also there is a lot of interplay between like mergers and all these disks between, for example, such as supernova 1987A or CSM supernova, which also have lots of material around them. But this is interesting because if we assume that there was indeed a disk and there are shocks here, but then the ejecta necessarily will be flying into the polar regions and we evolve the system for long enough, then something very similar to planetary nebula morphology arises in these cases. So some works actually explored this in detail for luminous red nova in our own galaxy. So for example, ALMA observations of the cold gas in these systems actually show that, well, this is like a 30 years old, I think is a 30-year-old luminous red nova in our own galaxy actually had this morphology. And by analyzing different properties of the different molecules, they came out with this model, which is actually a hourglass kind of bimodal morphology. And this was detected in the 17th century also as a transient. So right now, it also has this bimodal, maybe kind of jets or outflows. So this makes kind of a nice connection between this luminous red nova and like the geometries that we see right now. So what we are moving into is that we are going to have more and more of these luminous red nova. So we actually can start to use them to understand better the binary systems. For example, from the observations, we have these models, so we can actually use them to infer the ejecta masses. And if we have information about the progenitor source, we can estimate if, for different configurations, whether there was a full ejection or a full a merger, and somehow constrain this mass ratio. So this is what my PhD student is working on now. So we're trying to kind of put together all this information from the progenitor stage, going to this L2 mass loss, which creates the precursor emission and the properties of the outburst. So there is yet another interesting thing, and is that even if we don't have information about the progenitor mass, there is still a very tight correlation that was first proposed by Kochanek. I mean, the axes are reversed, be aware, this is mass, and this is the peak absolute magnitude of the luminous red nova, and here's the other way around. But there is a very nice correlation between how massive the progenitor star was and how bright it's the outburst. So we need to populate this more, but like at the moment, the correlation looks really nice. So even if we don't have information about the progenitor and archival data, we still can make some inference about a possible range of masses by looking at these correlations. So we actually can understand farther away luminous red nova where we don't reach with HST, for example. So the final project that we can do is just to compare rates. And this is something that we did with my colleagues at ZTF. So that was a census of the local universe, meaning that anything closer than 200 megaparsecs associated to a galaxy closer to 200 megaparsecs will receive a spectrum. So with 80% completeness, we computed the characteristics of all these properties of these outbursts that we would see. And if at later times they would show this molecular absorption, that meant that the ejecta was cold enough, meaning that they were luminous red nova. Then we computed some template light curves and rerun kind of the whole ZTF survey with the different luminosity functions to estimate the rates. So then if we put these rates into context, this was the same Kochanek paper from 2014, who used 3 objects in our galaxy to infer the rate. But yeah, the rate was not very reliable because these objects were in our own galaxy. They were also discovered by chance, many of them. So it's not a controlled sample. And this other work actually used binary population synthesis to predict the rate based on the properties of the initial binary, the ejected mass, and they used also mostly the hydrogen recombination to convert that to luminosity. And they predicted basically that we would have no detection of like these high luminous objects. But then what we see is that there indeed are these luminous red nova, which are like of higher luminosities. And these are the ones that could not be described by pure hydrogen recombination and needed the shocks. So this is the work that we are working with Rob actually, and let's say, can we do better? You know, if we use actually the shock modeling here, can we explain with binary population synthesis this missing bright luminous red nova that we are seeing? So then the future steps is, is to keep observing with instruments such as ZTF, for example, a huge field of view as compared to the predecessor. But there is also new surveys that are coming online. So from Palomar as well, there is this near-infrared survey called Winter. And the goal is to observe kind of a sample of galaxies, nearby galaxies, to look for these obscured full common envelope ejections. So the ones that we're not able to catch in the optical because of all these dust obscurations. So this is going to hunt for these kind of obscured events. And from the south, well, there is the Black Gem survey. And the very interesting things is that, because I joined as a PI of the Luminous Red Nova group, we agreed that the survey will target 3 times a night, most galaxies, which are within 15 megaparsecs that already have HST data. And this is great because that implies that, now this nearby M101 supernova was discovered by Itagaki, right? It's an amateur astronomer. And because ZTF observes like every 2 days, other surveys do every few days. But, for very nearby galaxies, if we look at them 3 times a night, we will be Itagaki, right? So we will actually, we will discover the supernova before he does. Well, of course, he's in Japan. Well, that's a problem. But depends on the pop-up of the supernova. But yeah, we actually will look at those galaxies as often as we can. So if something happens, we will be able to say straight away that something blew up and we will have the progenitor source. So then we can actually put all the story together. And of course, LSST, 2024 maybe, it will go so deep, so it will actually provide us all the information about the progenitors. So we'll be able to follow the sources up like for many years that it lasts. And if something blows up, we also will be able to rewind in the LSST beautiful multi-photometry bands to actually find out what the progenitor was and how the precursor emission brightened up, and maybe detect that period that we saw in V1309 SCO and we haven't seen in any other system. So that will provide the ultimate link in like massive stars between L2 mass loss and drain of angular momentum. So yeah, I'm very excited. I'm very excited because it's a great time to be doing Luminous Red Nova. And because right now, with something like Black Gem, ZTF, Atlas, time domain service, we have this little bit. We only see things when they pop up and we see the outburst in the optical and then they disappear. We only see this, and this is just the tip of the iceberg. With LSST or this high cadence in ZTF, we'll be able to actually find the progenitor source and see how it slowly brightens just before the outburst. So we actually can learn more about like what are the processes that are driving it to the merger. And finally, and I haven't talked about this much, but there is a lot of dust formation in those systems. And now is the right time to study it because we have JWST. So that in all these nearby luminous red nova that are nearby galaxies, we not only can see them during the optical, but we can also follow them up and see what kind of dust is produced. And because we have the rates, we can actually relate, the dust production mechanism by this type of transient to the total dust constant in the nearby universe. So it's an exciting time. So my conclusion is that, well, the common envelope is a highly complex but very interesting phase in binary evolution that it's needed to create complex binaries. But right now, the theory kind of looks at each part separately because it's very complex to simulate everything together. But we're lucky because we have luminous red nova, which is the observational kind of counterparts of these common envelope transients. And right now, we are in the right position to study, for example, what are the progenitors, when binaries become unstable, which binaries become unstable. Also, we will see this precursor emission and study how perhaps it's related to, the periodicity of the system. And finally, we also study the properties of the outburst and the late time remnants. So, well, these are the acronym of my ERC projects. It's Common Envelope Transients, 3P and O. So, yeah, thank you very much. And I will be happy to take any questions.
Thank you, Nadia. So, any questions from people here? Yeah.
Well, one is making a comment, very interesting presentation, and you're very clear about the relation on thank you very much.
Thank you.
Thanks. Any other questions from the public here? Yes, Mama?
Just very ignorant, and things like that are very clear and understanding. So do you have any either prediction or detection for plants, I don't know, to search for those things in other wavelengths, large field of view instruments that will be available soon, either in radio, for example, or in X-rays?
Yeah, the problem is we don't see any of those. So we don't see X-rays and we don't see radio.
You don't see, but this was carefully looked for, because if you have a shock and ejection,
yeah, I think that I talked with some theorists, and the prediction is that the radio is very low, because the shocks is not like in nova. It's not thousands of kilometers. It's just like 100, 200. Well, maybe 1,000, but yeah, let's say the shocks are really mild here. So they are not enough to power a very strong radio emission. We did follow up with radio of some of these M101 luminous red nova and some others, but we don't see anything. X-rays, I think there has been attempts to see X-rays and they all failed. So I think there's a lot of extinction in there, lots of dust obscuration. So probably it's eating most of the X-rays, and then the shocks are not powerful enough for radio. But we may be surprised. I mean, we should keep looking, but let's say, yeah, the attempts for now were not successful.
Did you try, I mean, in the context of what you were showing, that you were looking at those variability in those transients to try to see what they are, and sometimes they are other things, of course, if you might have. Have you ever, if you tried statistical analysis to match those with GRDs to see any of GRD progenitors actually were in your data, and you see something similar?
Oh.
Long GRDs.
You mean these ones? The one in our galaxies? No. This? No.
The one you showed that was, for example, the maxi source.
Ah, yeah. This.
Yes.
Well, we looked at the X-rays for the sample of 21 objects that looked evolving slowly from Milky Way stars. And only this one had a counterpart in Swift soft X-ray catalog.
Yeah, I was actually thinking more in all the galaxies.
Yeah. No, yeah, that's why, yeah, Hugo is now compiling the catalog of yellow, stars, which are hopefully Hertzsprung cap stars, not too many contaminants. So then, yeah, we can start looking at them once we have the catalog. Yeah, we don't know which stars are there yet. work in progress.
I don't think we ever, I mean, there was one claim at certain point, but I don't think there is any certain detection of a progenitor
Mhm.
detected in the data before.
Yeah, but this is very near. I mean, the catalog is going to be 50 megaparsecs. I don't know if there's any GRBs at 50 megaparsecs.
See, there are some. It's
Yeah, okay.
just
Well, Hugo has background in X-rays. I think he gave a seminar here like maybe a few months ago, but yeah, so the other plan is to cross-match these yellow sources with X-ray catalogs that he has compiled during his PhD to see maybe if there is some X-ray emission, maybe there is a compact companion there. So then it could be a luminous red nova with a compact object, which would be especially exciting. So. Mhm.
Any other questions? Yes.
One question about the simulation you showed by the people from
The hydro?
I think, right? Yes. Okay. So here, in terms of the microscopic physics in the simulations, in terms of because you mentioned that the combination energy would be important, I guess. So how complete are the simulations here in terms of that type of physics?
Well, it depends. Most are pure hydro, so there is no, there's no coupling with radiation whatsoever. Yeah, I think the new simulations start to include that, but it's a hard problem. Yeah, I think there's also Iaconi et al. They looked at also dust formation in this ejecta and so on, but it's the first one because it's a complex problem to form dust in this. So it's I think also it's a problem with the equation of state because the gas is not fully ionized. You have all these recombination fronts, so then you start to play into different opacity regimes, and this is not trivial. So then it's it's not it's a supernova are much easier, right? Like in the sense like everything is ionized, so you understand well all the gas properties, but in this case it's molecules, dust, ionized things. So it's not
it's a similar problem with the TVs now, right? That people is trying to model also the
Mhm.
for TVs. So I think that the combination also becomes important.
And here we don't have any relativistic effects on this. Yeah.
Any other questions? Yes.
Thank you very much, Nadia, for coming to the institute and giving this
Well,
nice,
happy to be here.
nice talk. But following this cartoon, is possible to resolve the binary system because on this side, we know that in the past several years ago, it was almost impossible to resolve with an image the binary system and missing AGVs, planetary nebula, protoplanetary nebula.
I mean, it normally will be resolved if it's a very close by system, right? Like galactic system. I know there's some interferometry that actually kind of resolves, but in external galaxy is going to be very, very hard. Yes. Yeah.
I'm missing protoplanetary nebula.
Yeah.
I don't think you really see a clear case resolving the binary system with this bipolar. I believe the model works, but I think we need to detect and to image the binary.
But at which stage? The
TVs,
yeah.
TVs in binary, protoplanetary nebula, preplanetary nebula. This is great. Because when you're not in the planetary nebula, they have this bipolar outflow, very well coordinated. So I think the best model is that you have a binary forming the abyss around the low mass star. But probably because the binary is very close, at the moment it's impossible to catch. We know that most of the stars form binary systems.
Yeah, I mean, what people did is they looked at the light curves of planetary nebula central stars, And that's how they found these 20% of binaries, because they had eclipses, and I think they kind of accounted for the, angle of observation and so on, and they extrapolated to 20%. So, but yeah, I mean, that's how far we can do. And yeah, then the presumably is that, yeah, there is indeed a disk here. So that's why there is this bipolar morphologies. And of course, I mean, maybe this is caused by fallback and accretion, so then you have like some jets. If there is a kind of a fast spinning core of the merger product, which are highly magnetized as well, highly rotating, so then we may power some jets which can actually pierce through these lobes.
Any other question I have on non-scientific question?
Go ahead with your question.
And that first beautiful picture of the binary stars, is that from like a series or a show?
You said it was from NASA, the one from the beginning.
Oh, yeah. I think this is for the Kepler, yeah, like those planets around the binary that. Yeah.
Oh, it's from NASA.
Yeah, it's an artist impression of how it would be to live on one of these planets around the binary system.
Do you have an estimation of how many objects are missed by extinction?
Yeah, that's a good question. I think this, like looking at this, looking at this work, I guess it's mostly for low mass systems, but these are the most common stars. So, probably a high percentage of these are actually obscured. So one of my collaborators is actually working with this NEOWISE mid-infrared survey. So he's looking for transients in the mid-infrared. He has many mid-infrared only transients in our own Milky Way that have been never detected in the optical. So the problem is that, we have light curves, but we don't know what they are. There may be, some obscured stars, maybe young stellar objects, but yeah, if we could not follow them up during the outburst when they were like maybe brighter, or we don't have access, well, maybe JLST, like a mid-infrared spectrum. But yeah, we don't know. We have many candidates, but we need to make sure that we understand what those outbursts are to quantify if they are indeed these systems.
And do you expect that evolution is different?
Yes, absolutely, yes. Yeah, thank you for the question. And it's like, when you have a main sequence or a yellow giant, basically, these mass laws, when you actually enter the envelope it has a much steeper gradient in density than if it would be like a HB or red giant. So then the process of the merger takes much shorter, as I show like this, the observations that we have is like few tens to a year time scales, but for red giant and AGB, it's years. So this also makes it difficult to detect in time domain surveys. Like now we have longer baselines, but normally you observe a field for a year and then you move on and so on. But now we start to have this longer baseline, and you would indeed see very slow increase in luminosities because you are entering a very low density envelope and you're spiraling in, and it takes years. And then there is something I didn't talk about, and that's what it's called the self-regulated phase. So you kind of, you enter, you stir the envelope, and basically you kind of puff up part of the envelope, and then you carve an empty space, right? So the secondary is just orbiting. You have gas above you, you have gas below you, but then there is a gap. And it's not until this gas kind of starts to fall down that you can kind of proceed with the spiral in and then enter in this dynamical ejection. So then if this like self-regulated phase exists, which we haven't observed yet, we are hunting for this, then this can add the timeline, it may be like maybe a century that for, the common envelope actually take place. So that's makes it again more difficult in detecting them.
But also, since these are like very low mass, they're also dimmer, so it would be you would probably have a huge bias there.
Yeah, exactly. So it's difficult because Kochanek used 3 objects, but they were found I don't think 2 of them in Ogle, and two of them somewhere else by amateur astronomers. But in ZTF data, we have like gazillions of galactic outbursts. And yeah, one of the goals is like my future PhD student will actually look for luminous red nova that we missed. Because now we all hunt for extragalactic things because they are in galaxies, and we know the distances. So we're very happy that we know the luminosity. So we know it's more or less a supernova, it's if in the gap or it's a nova. But for galactic sources, like sometimes Gaia does not provide like reliable parallaxes. So we don't know if it's in the gap, if it's not in the gap, what the hell is that outburst? And by default is ignore. So yeah, we need to go through all the archive to see like if there's like things that were luminous red nova and we missed them because of the light curves or other properties. So that's our future project.
I think we have time for one or two more questions. People online, are there any questions? Like, can you check the chat as well? So there's nothing.
No.
Okay. Any other question here? I just have one last question then. So you talked about LSSD, but I don't think SB has the the cadence already. Because you have all different topics. People that want to do science with SSD. So like regarding transients.
For
you think
supernova,
that's
it's going to be
useful?
horrible, but for
Yeah.
these, it's like 5 years. Even if it's every 2 weeks, a different filter, you just interpolate.
so-
And then my precursor like for years. So for me, LSSD is great.
Okay,
For
so it
supernova people,
doesn't
it's
matter.
garbage. I mean, like, yeah, that's why I need black gem, I need ZTF here in the bright phase because of the cadence.
Yeah.
But LSSD will be wonderful for this. Can fit any SCD, any black body, any stellar atmosphere model to the precursor data. And like, so for me, it's gonna be awesome. $5, I don't complain.
Okay, so yeah, thanks again, Nadia, for this talk. Yeah, you want to go to the patio and go to the.
Okay, thank you.